Alright, so do you guys watch the video on YouTube channel, previous one? So we're done with the chapter 10 on Wednesday, so I'm gonna move on to chapter 11. This is the last one, so we're almost done. So let's finish with the chapter 11 by next Monday. My plan was the covering, actually do a review session for exam two times, like Wednesday and Friday. But did you guys know next Wednesday is Veterans Day? So I only have a one review session. That will be kind of too short for the covering whole chapter 6 to 11. So my thinking was I might post the video on YouTube anyway on Wednesday. So I don't know, it's holiday, but you can still watch it. So you can have another time on Friday to just do the review. So you guys actually be here next Friday to do review, but you can also watch the one on Wednesday one that I might post on YouTube channel. That makes sense, right? Okay.
What day is
Oh.
the next test?
So day is the week before the Thanksgiving. So obviously you're in the Friday
It's the same
part,
as
right? Yeah.
now.
So
It's with the lecture and lecture.
Right. So I think you'll be in 20th, right?
Okay.
I think it's the 16th and 18th and 20th. It's the week before the Thanksgiving. Is that right? Right? The next Friday is the 20th. Right. Okay. So Friday's part is just coming into the week of the exam, but it's Friday. So Monday comes in Monday. Wednesday part student comes in Wednesday, and so forth. So yeah, makes sense, right? Okay. Perfect. So let's do chapter 11. So chapter 11 is about nucleophilic substitution. And the elimination. So if you look at the textbook, this is a really nucleophilic substitution heavy chapter. So I'm not gonna lie here. When you study for the exam 2, just focus on this one more. There only very few questions from elimination, but a lot more from the substitution. So this is how I'm gonna manage the time for covering the chapter 11 today on Monday. So first of all, we need to know why this is so important. So if you look at the Reagence cycle, this is coming from the compound. Is the looks this way. Okay. So this is the malic acid, and you try to put it in more halogenation form. So you can put phosphorus chloride here with some organic solvent molecules like these. So what he had was pretty much the same, but just replacing this one with the halogen groups. So now it's chlorine. This one. Okay. So if that is the case, we can also try to do a hydroxylation on this one again using silver 1 oxide and also in water base. Okay. So in this case, we could have the original form again. Okay. So if you look at this one over here, right? This one and this one is the same, right? This one is the same. But the thing was, you still remember the optical property, right? When you shoot the polarized light to the sample, they may rotate the polarized light. So this was the negative, which is a lever rotatory. So this is counterclockwise is rotated. So these looks almost same, because we did the same halogenation, but we put it the hydroxyl group again with the hydroxylation again. But this one actually shows a positive, which is a dextrorotatory. But the specific rotation was almost same. negative 2.3, but this is the same, but it's positive 2.3. I don't know if it's recorded well. Yeah, it looks well. So that is the same compounds, but shows the different opposite optical property. So this is the wonder why there might be something going on here. Okay, so this is the change in the optical property, but the same degree but the opposite direction, and we're assuming there might be inversion of configuration, meaning R and S. You guys remember this one, right? So this is a kind of stuck point where we see, there might be some, there might be some cause to make this change, even though they seem in the similar compound, same compounds, but in a different configuration form. So this is why we start trying to coming out of the idea why it's happening and so forth. Make sense, right? Make sense? You good? Okay. All right. So why changing the optical properties and everything? We can give you a few more examples so you can tell why. Okay. So if we have some kind of compound, looks like this one, you can have hydrogen groups here, over here. Okay, we have this type of compounds over here, and then we can try to treat it with some the acetate. Okay, so it's like this one, and then what happens to this one is we look at the products carefully over here. It's the hydrogen moved to this position right here, and this one we replace by this one, but not here. So you see the bromine here is a leaving group located over here, but this will be replaced by this one, but not in here, but here. That's kind of weird, right? So this is the where you're gonna put this. And where you had a bromine as your leaving group is where as hydrogen are located there. Okay. So this is a bit weird, but this is the sort of the same thing we saw from the previous example here. So this is also change of the configuration here. If you think about this is 1, this is a 2, this is a 3. Okay, so this will show you this type of configuration over here, right? So this is going to be 1 and 2 and 3 and 4, but 4 is on the back, so this is the S configuration because it's going this way. You guys remember this way? Okay, and then if you switch the position here, this is the 1, 2, 3, but you have number 4, the least priority group on the Canning gold preload convention, so you have to do it in this side. So even though it's still going this way, you have to put it on this way, right? So it's still going this way. Good notice. So this indeed makes some the configuration change when you do this type of interaction here. So we call this is our nucleophile. Nucleophile. Okay. So nucleophile will replace the way you can have a halogen groups. So you can have in this position. So this is why we call this a nucleophilic substitution. So nucleophile comes in and makes the halogen group as a leaving group. So they will leave, and then they're going to bond to that position. But in that way, they're actually going to happen in the change of the RS configuration in opposite way. Okay. So let me give you one more example. I have so if you have how about this one? We have group over here. Okay, we have a bromine group over here, and we can actually do it with the cyanide anion. So we can treat it with the sodium cyanide. The anion part of this one, cyanide anion, will do also work as a nucleophile. So if I put the NU, it's just the acronym for nucleophile. So whenever you see this one, you can think this as a nucleophile. Okay, NU is acronym for nucleophile. So obviously, we'll do the same, but can you guys guess what happened to this one here? So it's pretty much the same thing over here. Okay. So this is going to replace where you can see the halogen group, but not on the same position, but in the other side. So they're going to have tack on this one, and then the way you had a halogen group, now it switched the height over here. Okay. So if you do this one again, it'll be 1, 2, 3. So it's going this way, but your least priority group is on up front. So we're gonna put it in the different direction. So it's just going to this way. Right? So 1, 2, 3 is going this way. So counterclockwise. But this is on the up front. But this number 5 always has to be on the back to look at for RS configuration. So if you put actually on this side, this is going to be R. Right? Okay. And now, I mean, you don't even 1, 2, 3. So that's nice. So this is the kind of a same example over and over. See, if you have a nucleophile comes in, do the nucleophilic attack on the compound where that has the halogen group, they show good substitution, but interestingly, they show the change in the configuration. This is something the previous scientists did that was kind of interesting. So they tried to find the reason why. So far so good, right? We good, okay. So we find that there's the case, and we wanted to find out the reason why. Here's the one. So we kind of named this one SN2 reaction. You're gonna see this one and it's in this way, but I really don't mind. So SN2 reaction, we can say substitution reactions. So the N stands for nucleophile, again. And S stands for substitution, obviously. So this is literally nucleophilic substitution. Substitution. Okay. But there's number 2. This is where we need to kind of recall what we learned in Gen Chem 2. So number 2 is the meaning bimolecular. Bimolecular means there are going to be 2 factors will affect the rate of the reactions. So the rate is simply meaning how fast your reaction is happening. Like, so they will show you the change in your concentration of reactants over time. That is what it really means by rate. So how fast your reaction is happening, how fast the reactant is being removed, how fast the product is being produced. It's pretty much the same thing. But anyway, the rate comes in this form, the rate constant K. This is not the same as we learned in the equilibrium constant, so don't be confused. But this is just tell you the constant for the rate from the relationship between concentration and the speed of the reaction. So that means you're going to have some 2 factors in concentration form that will affect your rate. So in this case, here's the form you need to remember. So nucleophilic attraction, like I said, any compounds, any R groups that has halogen groups, and you have nucleophile comes in. You see this is acronym for nucleophile, NU, okay? And then you're going to have R with the nucleophile, and you have an X over here. Usually they're in the negative form. We'll do this later, but only thing you really have to know is the nucleophile comes in, and substitute, they replace the halogen groups on the compound, and they become the compound and the nucleophile combined in the X. And this is halogen here. So if those are the case, the rate depending on those two. So we're gonna put this in this form Rx. This is any compound with the halogen groups and nucleophile. So the concentration of the compounds, the reactants, that matters. But also that matters is your how many nucleophile you have in the reactions. So this is the two concentration number will affect the rate of your reaction, how fast your reaction will be happening, meaning this reaction here. So we call this bimolecular, because you have two factor will affect the speed of the reactions. So we call this SN2 reaction. Makes sense, right? Okay, perfect. You guys doing so great so far. That's nice. So here's the case. Why is bimolecular? That's the key now. Why change the, like I said, RS configuration change. That's the key now. Okay, that's good. So here's the reason why. This is a bimolecular because they're not going to have there'll be no intermediate. So I don't know if you guys remember alkene plus HBr thing. We had a transition status 1 and 2. So you had like this one. This is later we're gonna do for SN1, but not like this one. They're only going to be one step. One step. All process will be done in one step. So if it's happening in one step, they don't have to have an intermediate, right? Because there's one transition state that will make your product right away. Okay, kind of makes sense, right? Okay. So here's the thing. So how's it happening in one step, and how's it making your R and S configuration change? Because the way they approach to the compound, so nucleophile for SN2. So this is the SN2 reaction. Keep this in your mind. Whenever I do SN1, I'll tell you when. But for this, as for SN2, whenever you have compounds, maybe I can say, let me draw more. Okay, I'm sorry, I'm not be like. I'm sorry. This is so anyway. So if this is a halogen group over here compound, so it could be anything R group, hydrogen. We don't mind. But this is the compound that has a hydrogen group, and then when a nucleophile right here comes in, and they're going to attack where the halogen group is. No, they attack the back of opposite side of the where the halogen group is. What is awful drawing, I'm sorry, but what you really have to know is this is a tetrahedral structure. So it's not like a tetraplanar. It's a tetrahedral structure. This is more like this way. So one other goes here, 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 and here. Okay? So they're kind of coming in this back. Then what it does in the transition state is now those three are on the same plane. And now they kind of stretch out because the halogen group and nucleophile attach at the same time. So those two are attached at the same time. There's no cleavage, the bond, anything. The only difference is that has additional bond added to this carbon right here. But those three groups are kind of squeezed in the middle. So in the same plane, right? So that makes some kind of a trigonal bipyramidal here. It's like there's some pyramid in here. So those are three on the same plane, but those in the like a 180-degree opposite direction right there. So this is why they're going into only one step, because they don't have any steps to clear this bond, and this comes in later, but it all happened at the same time. So if this is a transition state, and it actually kind of explains why, if the nucleophile comes in the same side of the way you can have a halogen group, but in the opposite direction, it explains why it changed the R to the S to the R. Because your addition of the nucleophilic will be happening opposite side of the way you are eliminating hydrogen. So then, now it's going to be more like, after this one, this one. So before you had the halogen group on this side, those three of the groups on this side more, because it's tetrahedral structure, it's not tetraplanar. But when it comes in the opposite directions, now in the middle, now it pushed onto this side, where you had this one goes away. So halogen left now, and now it can keep the tetrahedral structure again, but this is the more place they can spread out their tetrahedral structure. So they're coming in this side, and those three groups now on more the right. Here and here. So that actually explains why whenever you have an SN2 reactions, will actually going to affect the change in the RS configuration before and after. Makes sense, right? Okay, that's really good. So this is the reason why we call this SN2. There will be two concentration because it's happening only one step. So we call this bimolecular, and it's only going to attack the back side of the way you have a halogen group. So it shows the RS configuration change. So if that is the case, there's something what you can do whenever you have a when it comes in. Okay, you have some nucleophile like a Cl minus, for example, and you can come to this one, right? Okay, and then scientists try to examine how it will change if it's really coming onto the backside. What I mean by that is if you have a halogen group like bromine over here, but if this one is filled with the all R group, like all three methyl over here, which is quite bulky, right? If you write this one again, you can actually see this. Why is it bulky in this side? It's pretty bulky, right? So, but the problem is the SN2 reaction, nucleophile once again, like for example Cl minus, the chlorine anion or any nucleophile should come into the back, not here. But this is really crowded already, right? Makes sense, right? If this comes in this side, doesn't matter. It doesn't really matter. But if this has to come in the back side, that's why it changed the RS configuration. Bulkier that the three groups are on the compound, it's harder for this one to come into the reactions. Makes sense, right? So this will show you if you have a tertiary, because you have a three R groups with the halogen group, especially for bromine. This is the least reactive one with the nucleophile, and the second one is what we call neopentyl halogen forms here. So this is the second list, and obviously, if it's the secondary or primary, and methyl so forth, the less substitute carbon where you have a halogen group in that compound will be more reactive with the nucleophile because there's a less bulkier group around the carbon that makes the nucleophile comes in more easily to the back side of the way you have a halogen group. So reactivity goes on higher if you go from left to the right. So less substitute carbon than attach bond to the halogen group. The nucleophile in SN2 has to come in the back side. So bulkier that is will be harder, but the less is easier for them to come into the reaction. So I didn't write it all, but this is the tertiary pentyl, secondary, primary. Makes sense, right? You good? Okay. All right, you guys are doing so great so far. So there's a couple more things for this type of trends. Like you see, so reactivity goes higher when you have a less substituted carbon that bond to the halogen group, because that is easier for the nucleophile comes in and attack on the backside of the compound where to the halogen group. So if that is the case, there's a couple more things, the trend you need to remember. So once again, if you have I'm not really good at drawing today, but so whenever you have some this group over here and comes into nucleophile, so nucleophile is usually negative because the nucleophile always looking for something is positive. Normally they become like a negative over here. So what happens to this one is this one. I'm not gonna draw more. I'm gonna draw it more like in this way now. Comes in the back. It doesn't say in the textbook that way, but this is what really happening in SN2. And then you're going to have X that is negative charge, because when they break apart, usually the halogen group are pretty highly electronegative. They can get those electrons when you break the bonds right here. So this is actually bond to this one. It goes into neutral now, but this one will become negative again. But you have another one. And sometimes, if it's not really negative, somewhat negative, so like its formal charge-wise is still kind of neutral, they can still do this, no problem. But this will become positive because they have donated the pair of electrons, but they're actually from the neutral status, so they can still do probably somewhat, but the thing is, obviously, this is not quite stable as much as this one, because they carry another positive charge on as a product. So normally, in generally speaking, this reaction is more common and more reactive than this one. But this is indeed possible. So whenever you look at the nucleophile, if it's not negative, you may still need to think there might be possibility that might do the SN2 reactions, even if it's not negative. But most of the time will be more in this case, and this will be more reactive than this one. But only difference is how they distribute the charge onto the outcomes, like leaving groups and your products. Makes sense, right? So only thing you really need to know is this is more frequently happening, more likely, and more reactive than this one. But these two are the possible scenario for SN2. Okay. Can I move on? I'm good. That's good. Okay. All right. So if you look at so this is about more like a nucleophile perspective. But as mentioned, SN2 also involves not just for the nucleophile, but also your compounds, right? Then your leaving group is also very important. So if your leaving group is better, then the reaction will be much faster too, because the leaving group will be more easy to leave from the compound, so they can have nucleophilic attack more easily happen on the carbon or the compounds. So leaving groups is simply, what I mean by this one is whenever you have like this one before you had a nucleophilic attack, this is a leaving group. So either this is the chlorine, fluorine, like the iodine, or the hydroxy group, or anything. It's just okay. But anything that kind of leaves the compounds that makes the nucleophile attack, in addition to that, the compounds, there's X, there's mostly halogen actually, but we call those the leaving groups over here. So we have some like experimentally proved some order. So if you have some like a like a hydroxy groups or amine groups or the ether groups, they're not really good leaving groups. And also it goes up if you go down from the column in your periodic table. So if you look at the column, you see this halogen, fluorine, chlorine, bromine, iodine over there, right? So this one goes even higher and higher, higher and higher. If you go down, down, down on the periodic table, simply because if you go down from the column in the periodic table, that means your size of the element is getting bigger and bigger and bigger. And then amount of the electrons are stored in the most outer shell or in the inner shells from the nucleus in that element is getting longer and longer and longer if you go down and down, down, down. So that means those electrons are much less tightly held by the nucleus in that element. So that means they're going to have a weaker and weaker and weaker and weaker bond to the compounds that makes better and better and better and better leaving groups. So think about the fluorine. Fluorine is the very small elements. If you look at the periodic table, it's very one of the few the small elements in the universe. So if it is bound to the carbon, this might be a bit more tightly bound to the organic compounds because the distance they can share the electron from their two nuclei from carbon and fluorine. But for those ones are getting bigger and bigger and bigger, they should have less force. We can have some less strength to put the electron having the same space because it's larger, which is longer distance from the compounds and the halogen group attached to it. So we'll have a less force can hold the electrons in the same space because it's covalent bond, but they can be easily broken if it has a longer and longer and longer distance. They can only practice the smaller force of the electrons to hold on to it, make those better and better and better leaving groups from left to the right. And those are the ones is the not so good one, but halogen groups is usually good one. Except I think chlorine maybe, but there's chlorine, iodine is pretty good leaving groups because of that. I hope that makes sense. It kind of makes sense, right? So, any questions? We good? Oh, perfect. You guys doing great so far. So, if that is the case, there's only one more thing I think I need to go over. Yes. So, like I mentioned, the hydroxy group is not a good leaving groups, right? Like I mentioned before. So, what you can do alternatively, I hope you guys watched the Monday lecture on which like 2 days ago. We just did in chapter 10 in the last part of the chapter 10. So whenever you have a hydroxy group which is not so good leaving groups, right? Not so good leaving groups. I'm gonna put LG leaving group. So the case what you can do is you can switch it to the better leaving groups. So what I mean by that is this is actually to kind of review what I did already on Monday, but this is either primary or secondary alcohol. So any compounds that has a hydroxy group, like OH, like hydroxy group, we call it alcohol. This is one of the things we did on the halogen part in chapter 10, how we can halogenate the alcohol. And like I've said before, the less substitute that the alcohol is, the harder to replace that hydroxy group by the halogen, which is here in our better leaving groups here. So what I mean by that is it either doesn't matter, either one. So maybe just one primary. It has this one. This is, for example, so this is a primary alcohol, either primary or secondary, it doesn't matter. This is once again, it's really not good leaving group. So if you picture it with the chlorine right away, they will not do much of a job because like I said in the trend before, right? This is the least one, right? And the far left one on the the leaving group order, right? So what you can do instead of just the nucleophile attack right away, you can do it with the other compounds like SOCO2. Then you can try, what you can try to do is they actually switch to, so this is what happened to this one is the SOCl plus SOCl minus. So those the two break apart. They break apart. So this will attach to when it's, so once again, oxygen is more electronegative than hydrogen, right? So it goes on here and positive, right here, right? So then you leaving the zinc ion, but this becomes the negative charge, and so they bond to there. So so if that is the case, they're going to have this right here, this one, okay? So this one is, so you have this one here, and this one bound to this compound over here, right? And this one is better leaving group than previous hydrogen group here. So eventually this will be replaced by this one, by this one. So now this is better, goes in and just go. Oh, so I mean more precisely, you're coming in this way, so you can push those all, but I'm not gonna do it in here because you guys already know. So this is the other way you can do the similar one. Makes sense, right? So we did this one because to make this the not so good leaving group to the better leaving group. So now then the nucleophile comes in to the more easier attack on this compound. So you can have this product, which is SN2. Makes sense, right? Okay. So just one more thing. It's very simple. Oh, I should. You can do the same with the this one. So maybe you can have my primary alcohol right here. You can do phosphorus tribromide here, and what it does is they also do the same, but it's they actually replace by this PBr2, and bromine comes in, and this makes the better leaving groups again, and it goes right here, so they can have. So it's pretty much the same. There's a lot of things you can do with the this one. All right, so there's the really famous, the best leaving groups among those all, even better than the iodine, is what we call tosylate. Tosylate groups is the best leaving groups. So what you can, tosylate is actually looks like this one. So you have so this is the tosylate leaving groups. So this is obviously the best leaving group. This is the best leaving groups. So, wow, 40 minutes. Okay. So what they do sometimes is they try to make this leaving groups by treating the alcohol with the this one. So you have And then you can try to get the replace this one by this one. Okay, so they can have this form. So this is another way to do the same, but this is quite important in this organic chemistry because this is the best living group among all the other living groups. So this is the quite common compound you use to make this kind of not so good living group switch to the best living groups. So later you can come in and you can have a substitution by nucleophile more easily. So this is something you can think about as the compound that has the living groups. If that compound doesn't have a good living groups, you can have some alternate way to replace it to the better living groups, and then you can do the nucleophilic type more easily. If it already has a good living groups, you don't have to do it. But in case you don't have really good living groups, for the SN2 reaction, you can do those previous alternate ways to replace the not so good living group to the better living groups. And Tosled is the best one. So this is specifically, I want you to remember, we normally put this in this form, or in this form. But we call this Tosled groups, which is the best living group you can use for the SN2 reaction in experiments. So this is all we need to know for the living groups. That's pretty much it. There's a few more things I need to go over. Can I do a little more? It's always 4 minutes. So why does it really matter? The living groups and everything. Because they actually makes if you look at the energy diagram over here, maybe we have some type of reaction goes on here, and this is only happening once in one step, so you're going to have only one transition state. Only one transition state over here, and then if this is possible, it's better if you have the higher in energy in the reactants, because the same transition state, because they will make lower in activation energy. So activation energy, you guys remember this? The activation energy is the amount of energy you need to have for the reaction going forward. But if it's lower in activation energy, the reaction will go much easier and faster because they don't have to have much of energy to proceed on the reactions here. So in that way, there's another thing they talk about is the solvation. So solvation simply means there is some solvent molecules will surround this compound in the reactions here. If you're using polar protic solvents, it's like alcohol or anything like some amine groups over there, they are able to make some like a hydrogen bond to the compounds. So that makes your reactions more stable. That means much lower in energy status. That makes the higher in activation energy, so it will be harder for the reaction goes forward. What we normally do in SN2 reaction is we use a polar aprotic solvents. So that means this is the solvent molecule that is polar, but they don't show the major hydrogen bond to the compound. So they can actually keep more compound in the solvent more unsurrounded much, not strong much. So then have a much more high in energy at the start point they only need to have a little bit more energy to go over the transition state, which is activation energy curve, the heel. They can go much faster here. I'll just stop here. I'll show you on Monday what are the ones we can add. I'll use the best polyprotic solvent so you can have a best possible S interaction in those conditions. Okay.